Okay, yeah. So today I'll be presenting about quantum chemistry simulation using VQE. So like if you have been interested in NISQ computing or NISQ, if you've taken some look in NISQ devices or something, you might have run into this kind of algorithm, VQE, because it's one of the most promising application of near-term quantum computers. So today I will briefly discuss about using VQE for quantum chemistry simulation. So the contents I'll be covering in this presentation are, first, I will just give some overview of the algorithm VQE and some of its motivation and applications. And next to the some part of the algorithm, which is the Hamiltonian representation, state preparation, measurement, and some sort of error mitigations. So
presentation.
Oh, presentation. Okay.
Your screen's here.
Okay, so what should I do?
Well, and then stop screen share. Kind of slow, right?
Yeah, seems good. Oh, it's working now, right?
Oh, yeah.
Where's the mouse?
Okay. Here. Oh, it's the next screen. Just go to the PowerPoint here, Microsoft. This one. Yeah.
I did this.
Oh, that's the. Okay. Okay, it's working, right?
Oh yeah.
Yeah, it's
okay.
working. Okay. Okay. So yeah, these are the contents that I will be discussing in this presentation. So yeah, let's start with, yeah, so what are variational quantum eigensolver? As we can see from the name, it looks like a self-explanatory. It's a variational quantum algorithm, which is related with eigenvalue problems, so solving eigenvalue of a certain matrix or something. So yeah, to give like a bit more specific definition, we can say that it's an algorithm that is used to estimate the ground state energy of a certain quantum mechanical system. But like in order to have a good bigger picture of the algorithm, we can just give it a mathematical definition. Like we can say that um, it's an algorithm used to find the minimum eigenvalue of a given matrix. So that matrix might be representing certain physical quantity. For this case, that matrix is like Hamiltonian of the given system. So yeah, we use the VQE to to approximate the minimum eigenvalue of a given Hermitian operator, or like the Hamiltonian, and it gives us the upper bound for the ground state energy or the minimum eigenvalue. So we can do this kind of eigenvalue estimation using quantum phase estimation algorithm, but it seems that quantum phase estimation requires larger circuit depths, which is not suitable for NISQ devices. So we are using the VQE or variational quantum eigensolver because it's suitable for NISQ devices. So when we say NISQ devices, they have some properties like they have noise, limited gate depths, and limited number of qubits. So it seems VQE is, even though there's noise in the hardware, we'll be able to get reasonable amount of reasonable result to be practically useful, which means the algorithm has some sort of resilience against this kind of noise on NISQ devices. And the circuit depth is also smaller, that it's feasible for NISQ devices. Oh, okay.
How does the quantum-based estimation methods estimate the ground state energy of?
Like the all about, like, if we have a certain Hamiltonian describing a certain physical system, so the ground state energy is like the minimum eigenvalue of that Hamiltonian, right? So, and a quantum phase estimation algorithm could be used to find eigenvalue of a given unitary operator, right? So if we describe the Hamiltonian at that operator and we find the eigenvalue of that Hamiltonian, it means we got the ground state energy of that, like that quantum mechanical system.
So what you wrote above is the description of quantum-based estimation.
This is like the VQE, just like VQE is based on variational principle of quantum mechanics. So we use the VQE to approximate the upper bound for the exactly like if we write the Schrodinger equation, we might say h times of the state phi equals e times of phi, right? So like if from the variational principle, we can get this kind of expression. So the minimum eigenvalue or the ground state energy is like bounded like this.
That inequality comes from the Schrodinger equation.
Yeah, we can say that, right? Yeah. Okay, and so we've seen what variational quantum eigensolver is, but so what is the motivation? So why do we need to study about them? So what are their practical advantages? So, we can say about the potential energy surface curve. When you have a certain molecule and so yeah, let's say that we're given this Schrodinger equation, and for a certain molecular system, we can plot the energy of that system at different distance. So just molecule is just a cluster of atoms and a space that with a certain distance between the atoms, right? And we can calculate the energy of that molecule using in this way. So if we and we can see that like the energy is dependent upon the distance between the given atom. For example, for the sake of simplicity, let's assume that we have two like a molecule with two atoms. So maybe we can consider a hydrogen molecule, and depending on the distance between the atoms, we can just represent the Hamiltonian in terms of the interatomic distance, so that we can get this form of energy function. So getting this PES curve is really important because it will allow us to compute the bond lengths and bond dissociation energy. So like and just we can say that a chemical reaction is all about like breaking and forming bonds. So if we can get this kind of energy landscape, we might be able to understand about the chemical reaction. And it was also important in like in drug discovery and also in material science and other applications. So the way we find this energy at this distance is using VQE. Using VQE, you can determine this energy value. So we can plot the whole curve by running the VQE algorithm at different distances. So in getting this PES curve is really important, and it has some sort of practical applications. Okay, that's it. And let's see the VQE pipeline. So the VQE is just a hybrid algorithm. It's not only run in quantum hardware. It's both done on classical computer and quantum hardware. So we can see from the figure, this color represents something that is done on the quantum hardware, and the blue one represents on the classical hardware and the classical computing subroutine. So we have first we have the problem. So problem is described into the Hamiltonian, just the Hamiltonian representation. There's some sort of encoding. I'll just describe about these steps later in the presentation. And in the quantum case, there is initialization of, we start from a certain Hartree fork state, and then we have a trial wave preparation using some sort of ansatz. And we have measurement. We need to measure the expectation value as we see from the equation in the previous slide. And this algorithm is run through an optimization loop, like by updating the parameters and so on. So what is the first one is Hamiltonian representation. So we have a molecule, and which is just a cluster of atoms separated by some distance in space. So we need to represent this physical system. So in order to represent that physical system, we need some sort of describe it with the Hamiltonian. So from the Born-Oppenheimer approximation, we consider the nuclei to be heavy. So they we consider them to be not to move. So we only need to consider the kinetic energy of the electrons and potential energy of electron and neutron attraction and repulsion energy. So the Hamiltonian would be described in this way. After that, we need to choose some basis to describe the Hamiltonian. And yeah, because just describing the Hamiltonian in this form might not be sufficient to solve them on a quantum computer. So we need a different way of representing this Hamiltonian. So there could be two ways, first quantization and second quantization. Both have their own advantage and disadvantage, but mostly in the VQE case, the second quantization is mostly used. Yeah, and in addition to the Hamiltonian, we also need to define some basis to express the electronic wave functions. So these bases, actually, there's a lot to talk about the basis, mostly, but there are a lot of basis functions, something like a Gaussian basis, plane wave, and some others. And using these different bases also have their own, they have their own impact on the accuracy of the VQE algorithm. So in order to represent the many body basis function, we have first, there's a Pauli exclusion principle, right? So the electronic wave function has to be anti-symmetric, which means if we try to exchange the particles, we need to get an inverted sign in the representation. So if we have a single basis function, and if we try to write them as a product of this single basis function, it might not be right, because when we swap them, we don't get the negative sign. So describing them using this latter determinant gives this anti-symmetric property of the electronic wave function. So, and this as latter determinant could be represented in other ways, something called Fock space. This represents that if phi1 is 0, which means it represents the orbital is unoccupied. If it's 1, it means the orbital is occupied. So these are, we choose some bases based on molecular orbitals and represent them using this way. So let's see about the second quantization formulation. So in the second quantization formulation, we describe the Hamiltonian that we saw in the previous slide in this way, in terms of the creation and annihilation operators. And here, the antisymmetric property is enforced on the construction of the operators rather than the wave functions. So yeah, like we designed the annihilation and creation operator in order to, in a way that they satisfy this antisymmetric and the fermionic anti-commutation relation. So yeah, here is the Hamiltonian representation, and these are called the 1 and 2 electron integrals. So they're like important quantities because they represent most of the electronic structure information is encoded in these integral values. So they could be computed easily in a classical computer. So yeah, and mostly when you run VQE algorithm, there are some libraries like the PYSCF something. They would like to extract this information from the electronic structure information from the given molecular description. So yeah, that's it. And the problem is like we have this Hamiltonian expression, but we're trying to evaluate the expectation value of this Hamiltonian, right? So we cannot, in order to determine this value on a quantum computer, this has to be written in some form of Pauli operators. So we need some sort of mapping from this description into summation of Pauli terms, because we can we can evaluate the expectation value of a given this kind of expression when they're written in terms of Pauli operators. So we need some sort of mapping from fermionic representation into a qubit representation. So we have several different kinds of mapping. The first one is, and the most popular one, is Jordan-Wigner mapping. So what Jordan-Wigner mapping is doing is, so we have orbital occupancy. I mean, this kind of description. One represents that the orbital is occupied, and 0 represents the orbital is not occupied. So this Jordan-Wigner mapping is direct translation. So if the orbital is occupied, we represent it by 1 in the qubit state. And if it's not occupied, it's represented by 0 in the qubit state. So, and this kind of mapping, we need to translate the fermionic Hamiltonian into a qubit Hamiltonian. So we need some sort of representation of the creation and annihilation operator. And this creation and annihilation operator also has to satisfy the fermionic anti-commutation relation. So yeah, if we represent them in this way, like if we represent them, for example, here, the creation is, if we have 0 state, it just change it to 1 state, right? But this kind of formalism doesn't work because it doesn't preserve the sign when there's some sort of the property of the fermionic anti-commutation relation. So we need to insert some sort of Z gates in order to handle this expression. Okay.
I think the AJ Dagger operator is, I think, 0, 1, 0, 0, I think.
0, 1?
0, 0. I think AJ Dagger and AJ is changed, I think.
Oh, is it flipped? AJ, oh yeah, sure. Yeah, okay. Yeah, that's right.
So it must be.
Okay. So AJ Dagger is, we have. That's right.
Yes.
So it means that. That's right.
I think.
Oh, okay.
I think it is.
Oh yeah. So yeah, I was trying to, if we construct this, it's going to be 0, 1. Oh yeah. Okay.
You think it is?
Okay.
That's actually 1.
This is 1. This is 1, right?
Yeah,
conventionally. Yeah, conventionally this is 1, right?
Yeah, so
this is 1 state. So if it's 1 and if we create it on 1,
zero state, it should be just zero.
Yeah, it's zero. It has to be zero. So yeah, I was considering like the creation operator is written this one, right? So if we write them once, sorry, this is has to be 0, 1.
It's 1 0.
1 0.
Right.
Oh yeah, sure. Sorry. So it has to be 0. 1 0. So am I not correct? Not sure.
Index.
Okay.
This is just problem convention.
Oh, it's
Oh,
convention.
yeah.
So okay.
Okay.
Sure.
Oh,
No
okay.
problem.
No problem. Okay, thanks.
Oh, no problem. Yeah, but like I don't know. Do we use this kind of convention to represent 0? I'm not sure.
The convention is actually opposite of usual convention. But
Yeah,
it
maybe
shouldn't
if
be
it-
any
Okay.
problem because
Yeah, it shouldn't be a problem. So like so I think you define this one as 0, right? As 0, right?
Yes.
So if it's 0, yeah. But like the way I define 0 is this one, 0, 1. I mean 1 0.
1 0.
Okay.
So yeah, if it's this way, yeah, then that's right. I think it's convention.
Okay.
It has to be flipped.
I think because of this, I think it would be
Okay.
and how much is it?
See, it has to be 0, right?
Eigenvalue.
What?
Oh, you mean the
Right.
eigenvalue? Okay. Yeah, okay. I thought, okay, the eigenvalue, okay, right.
Yeah.
That's right.
I think this factor gives 1. I think.
You thought.
Okay.
I learned about this.
Okay.
I learned this convention because 1 is 1, 0 is 1.
Oh, okay.
Yeah,
It's kind of
clock
different
out.
one. Okay, I see. So for this case, I think in this convention, I think we use the 0 state to represent this and 1 state to.
Okay, I think this is just reasonable because 0 is first, so 1 is first.
Yeah. That's something like as
Okay.
Okay,
no problem. Thanks.
Yeah.
Okay. So yeah, we can create the creation and annihilation operator like this, but this doesn't satisfy the what we call the fermiotic anti-commutation relation. So we represent this creation and annihilation operator in the following way. So this description cannot handle the what we call the fermionic anti-commutation relation. So we need this kind of description. So if we kind of plug them and try to do the calculation, we can easily show that the fermionic anti-commutation relationship, this one, will hold true. So yeah, this is the Jordan-Wigner mapping. And we have other kind of mapping called parity mapping. So yeah, it has some sort of advantage over the Jordan-Wigner mapping. In the parity mapping, so we have this orbital occupancy, 1 1 0 0 0. Like if one is, it's occupied. So the qubit state is encoded in a way that it tells us about the parity of the orbital occupancy. For example, here the parity is 1 1. Then here we have like it's just a sum of the number of ones before that qubit. So here, like the parity is 1. Here the parity flips to 0 0 0. So when a new electron comes, the parity flips. So it's the summation of the number of ones before it modulo 2. So yeah, this is how parity mapping is encoding this way. So we can translate the annihilation and creation operators in this way. So for example, if I wanted to create an electron here, so here, if we want to create here 1, like the parity and the next all has to be flipped, right? Because so that this X gate is doing that kind of operation. So when something is created here, all the parity next to the state are going to be flipped, and when there is occupation of an orbital, there's a difference in the sign. So this is handled by this operation. So and we can write the creation and annihilation operator this way, and after that.
I'm sorry, but can you explain again about Q?
Q, okay. So if we see here, like we have 0, right? Orbital occupancy is 0, means the orbital is not occupied. And when we get 1, the orbital is occupied. So when there's this kind of occupancy, there's some flip and a change in the parity, right? So in order to, if I wanted to create, like, let's say this is 0, and if I wanted to create particle here, then I have to flip all the states above the given qubit, and also because I'm creating something, so the parity is going to be for all is going to be flipped, because the parity determines like the whole sum of ones modulo 2. So if I insert something in the middle, then the rest of them has to be flipped.
So Q only have
this Q just changes the state from the previous and 1. Like the way I think it's written as something, it's an operation on both. I should have added some more description about this operator, but it's an operation on the previous and the current qubit. Okay. So like what is the advantage of parity mapping? It has some advantage because it will allow us to shrink the size of the Hamiltonian, because if we can see it here, we have like here, if we see the occupancy here, we have a fixed number of, for example, the one might represent the number of the electrons. So here we have 1, 2, 3, 4 electrons, right? So this number is conserved. So, and in the parity mapping, no matter what we do, the last bit is going to be 0, right? So it's one quantity that is there. So like there's some sort of redundant information encoded in this representation. So if we use the parity mapping, we might be able to reduce the size of the Hamiltonian, or taper the size of the Hamiltonian, because of this redundant information. We don't need to calculate some other quantities. So it will allow us to taper some of the qubits when using parity mapping.
Why the last qubit has to be 0?
For example, like we have, let's say a system has 4 electrons. So if we encode the number of ones, like it's even, right? Even parity. So the last here in this qubit representation, the parity is always like, no matter what the occupancy of the orbitals is, no matter, there could be different way of occupying these orbitals, right? But the number of electrons is always the same. That's 4.
Could it be like odd?
Because if it's odd, then we remove the electron from the system.
Why?
Because like 1 represents that orbital is occupied, right? So the whole the total number of ones represents the total number of electrons.
We have to consider about spin.
Spin, but like it's not a legit way of interpreting that way, but here, like for example, we have a system. We describe the orbitals, if they are occupied or not, with 1, right? If it's occupied with 1, if it's empty, then 0, right? So let's say our molecule has 4 electrons.
Okay.
So we have to describe if they occupy like the lower energy orbitals. Then in Jordan-Wigner mapping, we have this kind of 2 of the orbitals are not occupied and 4 of them are occupied. So even though we have different excitation or different configuration, we might have this, but still the number of electrons is always the same. It's conserved quantity, right? So yeah, like this kind of quantity is conserved, and parity mapping allows us, like when we encode it in the qubit, we can see that.
So we might have error.
Not error, but so like we have this kind of information and we have another information. So what we already know the total number of particles is always going to be 4, right? So in this state representation, the total number of 1 is going to be 4. Like no matter what the configuration is.
I think the question is what if you have 5 electrons instead?
5 electrons, so then it's going to be, but you cannot have that kind of representation in the solution state, because that is always conserved quantity, the number of electrons. We're trying to solve a state of a given molecular system, right? So like the number of, yeah, it's a conserved quantity. So,
yeah, I know, but what if that conserved quantity is odd?
Odd, yeah, it doesn't matter. Yeah, okay. So
but
then if
then
it's
the
odd,
parity should be 1.
the parity should be 1.
Also,
it means like we already know it, like
okay,
in the beginning.
Okay, so you mean like the redundant mean
Yeah,
we already know,
yeah, we
instead
already
of being
know this,
always
yeah,
0.
this kind of information from the beginning. So yeah, it's might not be right way of to say, but like just to have some maybe mathematically we can show that how peppering this Hamiltonian will have some benefits, but yeah, just intuitively like it's some sort of like redundant information that we have, so we don't need to calculate this expectation value on the whole Hamiltonian. If we taper them, then we can get exact approximation of from the previous Hamiltonian. Okay, yeah, so that's one way to taper, or like, so if we reduce the size of the Hamiltonian, which means we reduce the number of qubits required for the like simulating that molecule. So there's also other way of reducing the number of qubits, which is something called defining active space. Defining active space is, let's say in energy space, the molecular orbitals are described in this way. The Hartree-Fock molecular orbitals are described in this way, which means this is actually a water molecule. So in water molecule, for example, H2O molecule has H has 1 electron, so we have 2 electrons, and oxygen has about 8 electrons, right? So the whole molecule will have 10 electrons, and hydrogen is a 2-shell molecule, so we have 2 orbitals, 2 shell molecules, so we have 1 spatial orbital for H1 and 1 spatial orbital for H2, and oxygen has something like a 2-8, right? So we have about 5 orbital in the case of oxygen. So in total, we have 7 molecular orbitals, which are represented by this, from this to this, and the arrows represent the electrons. So in total, we have 10 electrons. So we have 7 spatial orbitals and 10 electrons, and each spatial orbital contains 2 electrons in that way. And here, when we define the active space, we can say that the lower energy orbitals, we can assume that the lower energy orbitals are always occupied by electrons. So yeah, because they have, we can say that they're occupied by electrons, and higher energy orbitals to be empty always. So if we define the active space to be the given broken box, we can reduce the size of our Hamiltonian. So we can just only spend a few qubits to simulate this. Okay, So this is all about reducing the number of qubits. So right now we have this kind of expression of the Hamiltonian in terms of a summation of polystrings. So if we have the Hamiltonian now, the next step will be searching for a trial state or for the ground state energy. So how do we search that? We use some sort of ansatz, which is a parameterized quantum circuit in order to search for the ground state energy that minimize the expectation value. So when we select an ansatz, there are some quantities that we need to consider, like its expressibility and trainability. We want our ansatz to be expressible enough to find the ground state energy or the state that we are looking for. And there are some common type of VQE ansatz, something like the hardware efficient ansatz, UCC type ansatz, and symmetry preserving ansatz. So yeah, like just even talking about this term also might like as it's a really broad topic. There's many to talk about these chemistry inspired ansatz. So, but it's generally they have their own properties. So like if we see here, we have this Hilbert space, and we don't want the ansatz to be like too much expressible, because if it's much more expressible, then we might need a lot of parameters to search for in the whole Hilbert space. So we can kind of constrain that ansatz to be looking for the solution in a given subspace, so that we can save a lot of energy trying to explore the unnecessary part of the Hilbert space. So we reduce the number of parameters used to search that space. So yeah, like these are one of the features of the given ansatz, like the UCC type. And yeah, so hardware efficient ansatz is, like it could be implemented on the hardware efficiently. So when we're dealing with some sort of noise, we might need to use this kind of ansatz, but it has its own disadvantage. And there's something called a symmetry preserving ansatz. This symmetry preserving ansatz, it preserves the number of ones and zeros in the given state. So it's not exploring the whole Hilbert space. So yeah, it has limited number of parameters. So it's one of its advantage. And this kind of ansatz also creates a way for some sort of error mitigation techniques. So the final step is measurement in the VQE. So like we have prepared the Hamiltonian, which is written as summation of polyterms. Summation of polyterms. There's some coefficients here, so it's represented as a summation of polyterms. And what we need to do is to evaluate this expectation value. So how we do it, that is we have several polyterms, and we find the expectation value of each polyterms independently by preparing different circuits, and then finally adding them up together. So this might require a lot of measurements, but there are some strategies to combine some sort of group, some of the polyterms together and measure them together. Because if we have two polystrings that commute, which means they can be measured simultaneously, so we can try to look for this kind of grouping strategy and reduce the total number of circuits required for the measurement, because the total Hamiltonian scales with n raised to 4.
So is there complexity analysis on how many measurement operators we need?
If we use, for example, Jordan-Wigner mapping, the size of the Hamiltonian scales n raised to 4, the total length of the Hamiltonian, total number of polystrings. So this is actually, it seems really bad. So maybe grouping them could reduce the total number of measurements that we need.
but like the order changes after we group the commuting counter.
The scaling order. Oh, I think, yeah, this, I'm not sure, but yeah, like, I'm not sure if the order changed, but it's kind of one way of reducing like the cost overhead, right? It's like the total cost over the requirement. So yeah, like group them together and reduce the number of circuit that needs to be measured. So this is the final step. So after we evaluate the expectation value, it corresponds to the energy. So if we are running it on a noisy quantum hardware, this expectation value could be far from the exact results. So we have to use some sort of way to mitigate these errors. So the two most common one are zero noise extrapolation and symmetry verification. Zero noise extrapolation, what it does is, if we have certain, like this is the circuit that we want to simulate, so we kind of scale the noise so that, for example, with this sort of noise, we got the expectation value to be here. And if we are here, for example, if we scale the noise to be large, we got the expectation value to be here. So, and if we extrapolate this one, we can get the value of the expectation value when the noise is zero. It's kind of some sort of approximation. And symmetry verification. Symmetry verification, yeah, if we have a symmetry preserving ansatz. What happened? PPT crash.
It was almost ended.
Faster than charging.
What?
I don't know. If you charge.
Oh no, I think.
It should be faster.
Okay, I think it's okay. I don't know. Maybe is it because it's. Sorry.
Maybe you have too many applications.
Maybe it's because of the HDMI. I don't know. Oh no. You can see it, right?
No, you didn't.
Yeah.
Share it.
By
screen.
Oh, okay. I haven't shared it. It's working, right? So, okay. I have to make it to presenter mode. Oh, it's not. Oh, okay. I have to do that step again, right?
Do you have many slides left?
No, it's fine, right? I just
then maybe it's okay.
It's okay, right? So yeah, like symmetry verification, and finally, yeah, this is the overview of the whole algorithm.
Yeah, actually, screen doesn't change.
Oh. How about I present it this way?
Oh, yeah, sure.
Yeah. It's changing, right? Oh yeah, sure. So yeah, this is the overview of the whole algorithm. We have the problem description in terms of fermionic Hamiltonian. It's mapped into qubit Hamiltonian, and then we search for the trial wave function through some sort of ansatz. And after we prepare the trial wave function, we do measurement. So in order to do measurement, we have to rotate in them into the given basis. And then we update the parameters in an optimization loop. So yeah, this is the whole algorithm, the VQE algorithm, and we could estimate the ground state energy or the minimum eigenvalue of the given Hamiltonian with this step. So yeah, that's it. And finally, its limitation. So the VQE algorithm, we can see that like the we can say that see that like the algorithm scales polynomially. So it's helpful to that there's some sort of advantage from theoretically we can say that this it scales polynomially, but the problem is does it really works in large scale or like in large molecules? So that is a question that is still unknown. So we're not sure if it's advantageous for large molecule or if it's really work in large scale. So the problem with that is due to, for example, like the VQE could be limited by just a large prefactor linked to the cost of accurate observable sampling. We need to do a lot of measurements to get an accurate in order to find an accurate description of the ground state. So, and that this could be one problem, and the other is it's all about an optimization problem, and we might not be sure that if the iteration could converge in a polynomial number of iteration. So yeah, it's kind of an open question also if VQE really converges in a polynomial number of iteration for all cases, because the VQE cost landscape seems solving that optimization problem seems to be NP hard. So in worst case, there could be some sort of cases where we cannot optimize it like with polynomial number of iteration. And like we're also not sure that how resilient it is to quantum noise. So we probably need error mitigation to get some sort of quantum advantage from VQE. And the problem is that error mitigation also requires some sort of cost. So it incurs additional resource for the whole algorithm, so that it might be really hard to get some quantum advantage from the VQE, but still these are some sort of an open question and challenge and using VQE for quantum chemistry simulation. And it has to be also more accurate and faster than the conventional computational chemistry calculations used to calculate the ground state energy of a certain molecular system. So that's it. Thank you for listening. If you have any questions. Okay.
How many electron sites can be capable in this method?
How
many electrons can be capable in this method?
Can you be more specific? Like how many electrons?
How many electrons can be solved by the
VQE?
Yes.
I think just theoretically, you will be able to simulate any molecules given with any number of electrons.
In practically?
Yeah, but practically they have a lot of limitation and challenge with but theoretically, so since if we have a description of the Hamiltonian describing the molecular system, so this problem is, or the VQE is all, what it is doing is changing that problem into eigenvalue problem. So if you can find the eigenvalue of that given the given description of the Hamiltonian, then I think we solved the.
Okay.
But so maybe you're trying to ask about ansatz something. Maybe it could be. Yeah, but like this is variational. Maybe like you're kind of mixing it with the conventional computational chemistry calculations for this case, right?
Yes.
Yeah, but this is kind of different way of solving the problem.
So in practical situation, we have the memory or the time limitation of computing. So
okay.
How many electrons can be solved?
Okay. So
about,
yeah, like
about how many?
Okay, maybe if I understand, do you might say to like actually solving eigenvalue of a matrix is not a big problem, right? You can solve it in polynomial time, right? But the problem with this is that the Hamiltonian size would be 2 raised to n by 2 raised to n. If we have like, for example, 10 orbitals, so the size of the Hamiltonian would be 2 raised to 10 by 2 raised to 10. So like we will run out of like the whole memory if we try to simulate more than a certain number of like electrons or orbitals. So I think that's one advantage of using the VQE. So it doesn't matter like yeah, because of in order, like classically we cannot compute if it's above a certain number of orbitals or electrons, we won't be able to have a memory to handle that large Hamiltonian size, right?
So like when you're simulating in-body physics,
okay,
the number of particles is very limited, like to simulate on classical computer
maybe,
without approximation.
Maybe in minimal physics, the electron number is infinite.
Then can you simulate infinite number of electrons?
No. Computer? Just like some little bit field theoretically treated. So we do not simulate infinitely, just finite size.
But you also have some approximations, like maybe in field theory. Is it right?
Mean field theory is not a kind of approximation, but in the renormalization concept, so we are only interested in lower energy, ground state energy. So we truncate high energy scale. It is maybe not kind of this approximation.
Okay.
We just truncate high energy.
Okay, yeah, just remove those high energy orbitals, right? Yeah,
it's
something like
similar with
gotcha. Okay, yeah, I see. Something this way, right?
Yes,
active space selection, right? Okay.
I think this approximation is very different kind of approximation.
Okay. So you reduce the size of the problem by ignoring those high energy orbitals, right? So, but like if theoretically, if you have many number of electrons, then which you don't need to truncate this, so it means it's not possible to simulate it, right?
Basically, you need exponential scaling
of the
so
memory in classical computer, but you need polynomial number of qubits.
The polynomial scale is very important.
Yeah, that's what actually one advantage of the using, because solving the like eigenvalue of a matrix will not be that because I think there's a way to decompose and solve it in polynomial scaling. So, but the size of the Hamiltonian will increase exponentially. So, in order to solve that problem, we're using the VQE.
So, have you ever seen about maybe spin chain or lattice the method can be for this kind of chain or lattice problem?
I think it has it has some sort of application for different formulation, but I haven't gone deep into the lattice model.
You can just change second quantization Hamiltonian to kind of Ising.
Heisenberg. Yes. This is maybe most important problem in physics.
Oh, okay. Yeah, that's right. Yeah.
The VQE is one of the most important applications for the computer, right?
For near-term scale, yeah.
For this.
Yeah, that's right.
So maybe, how about maybe some people just using this method to solve chain or?
Well, yeah, they are actually in the paper, for example. Like, yeah, there's for like it's not only for electronic structure problem, but this is actually the paper where it includes all the kind of the methods and the best practices in VQE. So like if we see the Hamiltonian description, we can use this for electronic structure Hamiltonian and also for lattice model. Yeah, like for other Hamiltonian models, like
there's Hubbard Hamiltonian.
Yeah, the Hubbard models too.
Oh, interesting.
So and vibrational Hamiltonian model.
My research area, interesting Hamiltonian.
Oh, okay. So that's I haven't looked so much about these kind of models, but for electronic structure Hamiltonian, yeah, it's just mostly studied because it has a lot of applications in drug discoveries and in material science and chemistry. So, yeah. Do you have any question?
Yeah, I think you. What is the symmetry? Can you go into the first slide?
Here?
I mean, in the last slide.
Last slide. Here.
Yeah. Yeah. What is symmetry verification?
Symmetry verification is okay. So if we have a symmetry, like we might have a symmetry preserving ansatz, right? So let's say we have some sort of different kind of ansatz, and what it does is, for example, if we are starting from the Hartree-Fock state, 0 to 1. So if it's symmetry preserving ansatz, then it preserves the number of ones in these states. So we have given 0, 1 state, then the output states will always be something like alpha 0, 1 plus beta 1, 0. So we can now get something like 0, 0 state or 1, 1 state in our final result.
So you mean it preserves parity?
It preserves the number of electrons or particles, like particle preserving ansatz. So yeah, it means like there's a symmetry between the input and the output states. So, and if you run this one on a quantum computer and there's some sort of noise, right? And we might, like if it's perfect, then from like our measurement statistics, we can only get 0, 1 or 1, 0, 1, 0 state. But if there's noise, we might be able to get 0, 0 state and 1, 1 state.
Then how do we correct it? We just project?
So yeah, just project that one, so we'll be more closer to. So like symmetry verification is that we verify if the output state is, since it's a symmetry preserving ansatz, we verify if the output state is within the symmetry or not. If it's not there, then we might say that there's some sort of noise, so we have to correct this, these wrong results. So if we project them into, if we construct a number of electron operator and project them that one and filter out these results, we can say that it converges to the like the ideal expectation rate. Okay, that's it.
Okay, so no more questions? No more questions from Zoom? Okay, so...
Okay, yeah.
Juan, you finish. Just a quick question. So I was always curious about what are some recent results in VQE regarding the size of the molecule simulated?
Okay.
So nowadays, how big of a molecule do you simulate?
Like I think yeah, I'm not sure. The largest molecule I've seen was maybe N2. I'm not sure exactly, but N2 or beryllium hydride. But yeah, I have to check this one. But it's all about the problem of the problem of number of qubits, and the other problem is like when we're trying to simulate a molecule with large number of qubits, we might not get a good result because of the circuit depths and kind of stuff. So if they don't get that reasonable result, I think they might not publish it. So it's not a problem. I don't think it's a problem of having lower number of qubits. Maybe result is not good for simulating.
I see.
Yeah, but I'm not sure. Like, not exactly sure about it.
Okay, thank you.
Okay, thank you.
So, when you talk about beryllium, hydride,
yeah,
that's like published in 2017.
Oh, yeah, that was on. Okay. I think there's a simulation in H2O. I think H2O requires more number of qubits than beryllium hydride, right?
Oh, yeah. Oh, really?
Yeah, I think so. H2 is beryllium is kind of special.
Oh, so they didn't freeze the core. If you consider only active electrons, then it shouldn't be the same.
Okay, yeah, it has to be the same, right? Yeah. Same number of I think they have the same structure with H2. Yeah. Same structure, yeah. Like basically they need the same number of. So yeah, maybe how about N2? Yeah, but I'm not really sure. Yeah, I've seen some simulation on H2O. Beyond that, I'm not sure. Like as far as I can remember, yeah, the largest molecule I've seen is H2O in hardware.
So there is no more question. Thank you for the high quality lecture.
Thanks for listening.
Okay, and see you next week. I mean next week.